I welcome Professor Dr. S. Jones, Principal, Albury Institute of Science and Technology. We are privileged to have you here in this platform of ASAP.
Today's session is on strain energy methods as part of the S4 mechanical course on advanced mechanics of solids. And this strain energy methods, before starting the topic, we should move through the basic definitions and regarding what is strain energy and how this concept is utilized in analysis of structures. Basically, when a load is applied on a body, that body is deformed. The basic thing. And when a body is deformed, it means some work is done. And this work is done by the applied load. And this work done is absorbed by the body as energy. That means some energy is stored in the body. And this energy will be released when the load is removed. That is when the body is deformed elastically. During the range of elastic deformation, this is completely recovered when the load is removed. And this energy is called as strain energy. Because when we apply the load, some strain is produced in the body and the energy is stored as strain energy. And when the load is removed, the body regains the original shape and size utilizing this stored energy. And the total strain energy, it consists of the elastic part and also the plastic part. So when the body deforms up to a certain limit, it is deformed elastically. That means the deformation is recoverable or temporary deformation. And after that limit, the deformation is permanent. It cannot be recovered. The deformation is done to the body on a permanent basis. That deformation is called plastic deformation. And the total strain energy consists of both these. You can see the stress strain curve where strain and stress are given along the two axes. And up to this point, we can call it as elastic deformation. And beyond this point, the deformation goes in a different pattern. And this deformation is permanent and it is called plastic deformation. So after this point, the material fails. And up to this point, we consider as the total strain energy. Total strain energy is a shaded portion in this curve. This curve is the strain curve. It is represented by the shaded area in the strain curve, total strain energy. And what we are considering in this study is not the total strain energy, but the elastic strain energy. The elastic strain energy is that part of the energy which is recovered. The elastic part of deformation only is recovered or cancelled. It is withdrawn. Once the load is withdrawn, the body comes back into the original size and shape. And that part of strain energy is called elastic strain energy. Here, this hatched area in the stress strain curve diagram represents elastic strain energy. And this elastic region, we can have different materials behaving in different ways. In cases like steel, the deformation can be assumed to be linear. The deformation and load or stress and strain are proportional, and we can have a linear curve for the stress strain curve diagram, or load deformation curve will be a linear one. In that case, we can say it is a linearly elastic body. So it is, that material is called perfectly elastic, and again it can be linearly elastic. This is linearly elastic material. Load deformation diagram for a linear elastic material, and this is for non-linear elastic material. That means the curve is not linear. It is not in a straight line. It is having a curvature. A non-linear behavior is observed. In both these cases, we can say the material is perfectly elastic. There is no plastic deformation, or we are considering only the elastic part of the deformation. So linear elastic or non-linear elastic. In both the cases, we can have the load deformation curve like this. And here, the light colored area, or the area marked as U, represents the strain energy, elastic strain energy. It is a area under the curve and the deformation axis under the curve defined by the deformation axis. And there is another area marked as U star that represents complementary strain energy. It is an area enclosed by the curve and the load axis, which is called as complementary strain energy, U star. These are the two notation used, U and U star, strain energy and complementary strain energy. So in a linearly elastic material, we can say U is equal to U star. Here, this is a linearly elastic material where both these are equal. So up to this level, we have seen a number of definitions. So when you are appearing for the examination, there can be questions based on these definitions. Elastic strain energy, complementary strain energy, total strain energy. All these are typical questions that may be asked to explain the basics. So this, when you are writing about the linearly elastic material, you should explain about the strain energy, then complementary strain energy, and this relationship also you have to explain. So in all the cases, you will be considering the elastic region of deformation, and elastic strain energy is being considered in the following explanations. Coming to the strain energy methods, and what is meant by a strain energy method, and how or why it is used. The major advantage of a strain energy method is that it is a scalar method, because energy is a scalar quantity, and we know what is a vector quantity and what is a tensor. So when you are using vectors in certain calculations, certain equations, you know what are the complications involved. And instead, if you are using tensor, again, for certain people, the tensors will be easy because it is easy for computation. Say some matrices are used and it is easy, but for an average student, tensor will be a difficult one. So here we need not use any tensor or vector. We will be using just scalar method, just like our arithmetic calculations. Only we need to manipulate the magnitudes alone. So it is relatively easier. And this method can be used in solving elasticity problems to determine mainly for deflection of structures. In your MOS class, you would have studied about different methods of determining deflections of structures. So based on different types of loading, different methods are there to determine the deflection. Types of loading means normal, say, axial stress can be applied, a shear stress can be applied, a torque can be applied, a bending moment can be applied. In certain such applications, the deflection of structure needs to be determined, and that involves different types of equations and solution procedures. And the same thing, the deflection of structures can be determined using the strain energy methods, using a scalar approach. And another, a major advantage of strain energy method is it can be used for statically determinate as well as indeterminate structures. Now, what is a determinate structure, statically determinate structure? Statically determinate means we have used equations like sigma fx equal to 0 to evaluate the forces acting along a particular direction. And this is used to ensure equilibrium in a problem of statics. And another equation used is sigma mx, that is the sum of moments about the point x is equal to 0 in equilibrium. And if you are able to solve a problem using any of these methods, we can call it as a statically determinate problem. And if it is not possible, then we call it as statically indeterminate. That is, using the principles of statics, we can solve the problem in a statically determinate case. In the other case, it may not be possible. These equations and its group of equations may not be enough to solve a particular type of problem. So these two types, both the statically determinate as well indeterminate, both can be solved using the strain energy approach. So these are the advantages. This is a major advantage, and this is one of the important applications, and this is another advantage of strain energy method. Now we will take a simple example of axially loaded bar. The diagram is shown here. A bar of length L is fixed at one end, this end is fixed, and a load of E is applied at the free end along the axial direction. And this load deflection diagram can be represented like this. The deflection or deformation is shown along the x-axis, and load is shown along the y-axis. And when you represent it like this, the deformation due to the application of load is, let it be dx. When the length is elongated by dx due to the load p, we can say du equal to p into dx. And this is evident from this diagram also. If you take this dx as a width of the small elemental area and height of that particular strip is taken as p, then that area can be approximated as p into dx. And the total energy involved in this case can be the total area under this curve. Starting from when the load is applied, it initially starts from 0 and reaches the maximum value of P. And during this time, the deformation occurs. So continuously it is varying. So this can be obtained as a integral of P dx. Is the let's say the total work done is given by integral P dx over the length x1 or L. So here it is taken as L. So integral 0 to L P dx. By integrating this, we can get the area under the curve. The area under the curve is defined by this integral. So we can write it like this, or we can write it as half P into L. So for linear elastic deformation, this curve will be a straight line. This is P and this is L. So area of a triangle is there, and that is given by half of P into L. So this is how we evaluate the strain energy of deformation. So in any case, we can determine this area under the curve by suitably representing this particular problem as an equation which is to be integrated. Now, another point which is connected with this is strain energy density. We have seen what is strain energy. Now, strain energy density, unless it is per unit volume, so is strain energy density. Strain energy per unit volume is called strain energy density. And another word or another term used for representing strain energy density is resilience. So the definition is just basic definition of, remember the basic definition of strain density. It is applicable in strain energy also. Strain energy per unit volume. So when we are using strain energy density in a calculation, the effect of size of the loaded bar can be eliminated. Whatever may be the size of the bar, size of the body which is loaded, it does not have any effect on resilience. But it is having an effect on, if you are taking strain energy alone, the dimension or the size of the body is having an effect. Now it can be defined as U by V. U is strain energy and V is the volume of the body. So U, we know it is P into dx. So integral of P into dx. If you are taking V also, V is area is cross-sectional area and L is the length. A into L is the volume. Now if you take it separately, P by A, it is nothing but sigma x, the linear normal stress. And what is dx by L? It is the elemental strain, the elemental length, increase in length by original length. It is an elemental strain. Now the equation can be integral 0 to epsilon 1, the total strain, the total length over the total length of x1, or L, the total strain is epsilon 1. So it can be integrated over the range 0 to epsilon 1. And you need not worry about the integrals. Only in this definition or in the definition or in the derivation of these expressions, we have to use the integrals. Otherwise, we need not go for any such things. So here, we are using the small u as a notation for strain energy density. So same expression by replacing sigma x by E into epsilon x. It is from Hooke's law. In Hooke's law, we know that in an elastic material, stress and strain are proportional, and E is the proportionality constant. It is the modulus of elasticity. So we can replace sigma x by E into epsilon x, and the epsilon x is already there. Now, this can be evaluated, this can be integrated to obtain this. And again, if we want, we can replace epsilon 1 square by sigma 1 square by E square. Epsilon 1 square is sigma 1 square by E square. This E and 1 E will cancel, and finally we will get this expression for strain energy density. So this expression also we have to remember. Strain energy density is sigma 1 square by 2E, or sigma square by 2E in a linearly elastic material. Now we will come to the general expression. What we have seen earlier is about a body which is subjected to only an axial load in a particular direction, in the direction of one axis. But if you consider an element in which the force is applied in a force is applied gradually. In the previous case also we have considered that one, the load is applied gradually. If we are specifically saying the load is applied gradually. Now the work done is force into distance by 2, because the load initially is 0 and gradually it reaches the maximum value of, say, P or some other quantity. So here the energy due to sigma x, that is load applied in the direction of x, is dy into dz, that is the area of cross section of the surface perpendicular to x direction. Area into stress, it becomes force. Distance is strain produced in the x direction into the length along the x direction, and these two together is the distance or displacement along the x direction. So force into displacement multiplied by half. It is the energy when a force is applied gradually. Now the strain energy, the contribution of strain energy is half of sigma x into epsilon x into dx, dy, dz. This is a volume. When this element is subjected to forces along all the three directions, here only one force is applied and only a normal stress is produced by that force, and due to the normal stress, a strain along the x direction alone, a normal strain along the x direction alone was present in the body. Now what we are going to consider is, we are considering forces acting along x direction, y direction, and z direction. And due to this, stresses will be developed in all the three normal directions as well the tangential direction. So sigma x, as you know, it is due to the load applied along the x direction. Stress of sigma x is developed along the x direction. Similarly, these two. Here, tau xy is the shear stress developed along the y direction due to the load applied along the x direction. And due to this shear stress, a shear strain is developed, which is called gamma xy. Similarly, these two are involved in the respective directions due to the stresses acting in some other direction. So all this together is used to define the strain energy due to forces acting along all the three reference directions. And here we'll be using a volume integral because we are integrating with respect to three variables x, y, z. And this is the general expression for strain energy. So when you come to an axially loaded body, the example which we have discussed earlier, this expression may reduce to this level. Only a normal stress is acting, sigma x, or a load is applied along the axial direction. Only this load is there, P is applied. Due to that, sigma x is developed along the normal direction. And at the same time, due to this loading, there can be a shear stress developed along the y direction. Due to the load applied along the x direction, there can be a shear stress developed along the y direction. And that may lead to a shear strain along the y direction. And this together can be considered. And here again, we will be using Hooke's law to convert the terms into a particular level. That is epsilon x, instead of epsilon x, we can write sigma x by E. Instead of gamma xy, we can use tau xy by G. It is also from the Hooke's law. The same expression we can use for cases like axial loading, bending, and shear stresses in beams, or torsional stresses. Torsional means torque is applied. In the case of axial loading, the loading direction is different. In bending, we will be applying loads like this so that the bending is occurred. In shear stresses, the loading will be suitable to produce shear stresses. In all these cases, we can use this general expression with certain modifications to find out the total elastic strain energy involved in that particular case. We can see how the strain energy due to normal stress can be developed. So this is a basic expression for elastic strain energy density, and this expression we already have seen, and within the proportional limit, this expression comes from the Hooke's law. So using this, we can write the strain energy density is half of sigma x square by E. That expression is also already explained to you. Now, this can be used in this expression, du by dv. That expression and this one can be combined to write like this. Du is equal to s into dv. And it can be integrated to obtain the total elastic strain energy. It is an elemental strain energy on the elemental volume. Even though we are showing a single integral symbol, it is evaluated or differentiated over the volume, integrated over the volume. It's just like a triple integral. And here we can put sigma is equal to P by A and dV is equal to A into dx. A is area of cross section and this is a length. Now the expression can be modified as P square L by 2AE. U strain energy, elastic strain energy is equal to P square L by 2AE. You may be familiar with this expression, PL by AE. What is it? Deflection. You studied this in MOS. PL by AE is a deflection. Now the energy is given as P square L by 2AE, and that is P by 2 is there. So you can write U is equal to half of P into delta. It is the same expression which we have seen earlier. Half of P into X, half of P into L. Like that we have written the expressions. Now it is half of P into delta, the deflection. And the same expression which we have seen, we have studied in MOS. The same thing which we are using here. So, strain energy is represented as half of applied normal stress, normal force into deflection. It is in the case of normal stress when a load is applied along the axial direction. Now we can take up an example, a problem. You can read this question. This is a typical problem which can be used, which can be asked for the examination. The case of a normal of a body applied subjected to normal stress. So here the cross-sectional area is given as 600 millimeters square and a length of 2 meters. If the stress at the elastic limit is 170 Newton per millimeter square, what will be its proof resilience? Proof resilience, you can take it as resilience. Determine also the maximum value of an applied load which can be suddenly applied without exceeding the elastic limit. Calculate the value of the gradually applied load which will produce the same extension as that produced by suddenly applied load that is determined earlier. So we are considering two cases, gradually applied load and suddenly applied load. And first of all, we will be considering proof resilience. Proof resilience, it is nothing but strain energy density. So here what is given is area of cross section, length of bar, volume of bar can be calculated, stress at elastic limit is given, modulus of velocity is assumed. And using this, we can determine the resilience, proof resilience, sigma square by 2E into the volume. And that you can determine, and that is one part of the question. And if the suddenly applied load is P1, P is the value of suddenly applied load and P1 the gradually applied load. For a suddenly applied load, we know sigma is equal to 2P by A. Suddenly applied load. Throughout the loading, the load is applied all of a sudden. Then we will consider it as 2P. And if you consider it like this, we can determine P from the values of sigma and A which are available. A is sigma is given as 170 and cross sectional area is given as 600. Using that, we can say 51 is the suddenly applied load. And if this suddenly applied load produces a stress of sigma equal to 170, it produces an extension or a strain of epsilon x. And we want the same extension or same strain to happen when the gradually applied load is given. When you are giving a gradually applied load, the conventional expression for stress can be utilized. When gradually applied load, sigma is equal to P1 by A or P by A, the value of stress which is applied. Normally, the stress is applied gradually. It's a load deformation curve. Gradually, the load increases up to the maximum of P1. And in that case, stress is equal to P1 by A. And P1 is not known, sigma is available, sigma and A are available. Using that, we can determine what is the value of gradually applied load to produce the same stress of 170 Newton per millimeter square. That will produce the same strain and same extension. So this problem utilizes only the basic principles. The basic principles used in this discussion. The only thing which we use here is the proof resilience, the strain energy density. That expression alone is used. There is nothing related to the what we call as strain energy methods. That we are coming to that topic only. We have seen the basics related to the strain energy density and evaluation of strain energy. How the strain energy can be evaluated, starting from strain energy density and the particular type of loading method which we are using.
What is proof resilience?
Proof resilience means resilience at the maximum value of that load which is applied. Resilience means strain energy density, and strain energy density corresponding to this sigma. So when you are gradually applying the load, the sigma value is gradually increasing from 0 to the final value. The load is applied gradually, starting from 0 to the maximum value. During this course, the stress sigma 1 or sigma is also varying from 0 to the maximum value of, say, 170 Newton per millimeter square. Proof resilience represents the value of resilience at this maximum value of stress, nothing else.
Which you have explained. How is the value of E obtained?
E is a standard value. It is a modulus.
In the question number 1, you have just explained. How is the value of E obtained?
Value of E is a standard value. It can be assumed when the question when it is not given in the question. Uniform, it is a metal. It is given as a metal, and we are considering the elastic deformation. And in that case, we can assume a suitable value for modulus of elasticity. Now we are going to consider different types of loading. Already you have seen the expression for strain energy due to normal stress. When a shear stress alone is applied, how the strain energy expression, what will be the expression for shear stress? When the pure bending is applied, what will be the difference? And like this, we can have different expressions for strain energy upon different types of loading. And these are the expressions. The first one we have proved. The proof has been explained. Using the same approach, starting from the basic principles, we can show that when a shear stress of tau xy is applied on a body of volume V, is a volume, G is a modulus of rigidity. Modulus of the rigidity of the material. It is a material property. So here the load is the shear stress. How much shear stress is applied on a body of volume V having a modulus of rigidity of G. Now in the case of bending, here it is m square. M is a moment which is applied. L is the length of the beam, and E is the modulus of elasticity, and I is moment of inertia. A similar expression you may have studied in your MOS class. Moment of inertia, I. EI is also familiar to you. So this expression can be used to represent, to evaluate strain energy in the case of a problem which involves only pure bending. Only a moment is applied. And in torsion, in a torsional loading, we will be applying a torque. A torque is applied to twist, to produce a twist in a body, in the loaded body. And here, this L is representing the length of the bar, and the G is a modulus of rigidity, and J is a polar moment of inertia. And this is why I have mentioned, you have to remember, you have to brush up those principles which we have studied in MOS. Moment of inertia, polar moment of inertia, modulus of rigidity, moment, torque, all these things are familiar to you from the basics in MOS. So here, these four expressions to be kept in mind. Using these expressions, we can solve problems in using the strain energy method. And now we are going to see how this strain energy approach can be used in solving problems. In the case of a problem, when you consider a particular problem, there can be different types of loads acting on the body. First of all, in this particular discussion, we consider only the cases where a single load is applied, not more than one type of load. Only a single load is applied on a particular body. How the deflection can be determined using strain energy method. That is deflection under a single load. The single load can be a loading like this. a point load applied on a
is I, area, moment of inertia of cross section.
I is moment of inertia of the cross section. I is moment of inertia of the cross section, and J is polar moment of inertia of the cross section.
Sorry, Y is the expression for strain due to shear force, different from all other three expressions.
So difference is there in this volume. So he may be asking that one. Maybe asked for the examination, but I am not explaining all the proof here because it will be a lengthy session. That is why the proof is not explained here. The proof is available in the textbooks. You can refer to that textbook and understand how these are proved. I have explained the proof about this one only. The first one is explained, and similar approach is taken for the remaining three. It is explained in the textbooks,
Okay.
and you can. It may be asked for the examination. The proof may be asked, but why I am not explaining this is it may not be easy for all the students to understand and reproduce for the examination. Only those who are having very good understanding about the MOS principles will be able to follow this. That is why the proof is not presented here. And also it will be a time consuming exercise. So here deflection is single load. It is included in our syllabus. We are considering only deflection, determination of deflection using strain energy methods under a single load. Here a load of P is applied, and due to that a deflection of Y is being produced, and this can be evaluated by this expression. A strain energy is equal to half of P into Y, and this is the case of a bending moment. A moment is applied onto the body, and the beam undergoes deflection, and that deflection is evaluated by the angle or the twist which is obtained, and this is evaluated, considered as a deflection in this case, where moment is a applied load. There we can represent the strain energy using this expression. Now the third case is a case of torsion. A torque is applied onto this circular bar. Once a torque is applied, the bar which is fixed at one end undergoes a twist of phi. So torque T is applied, and that produces a deflection of phi, which is the angle of twist. Here the strain energy is half of E into phi. So these three expressions we can use to find out the deflection. Once a problem is given, we can determine U using the expressions which we have developed earlier. Then P is the applied load is known to us. Using that, Y can be determined, or theta can be determined, or phi can be determined. This deflection can be determined. So the procedure is like this. Strain energy density is to be determined and to integrate to obtain the strain energy. Or if you are having a standard formula available to us, we can directly use to determine strain energy directly. And this can be used only for single loads. The method is also called as work energy method. Most important one, this approach, work energy method, cannot be used for members subjected to several loads. Only a single load is applied. In that case, we can use the work energy method. Can we have some more time to explain this problem also? Also involves a single load. A load P is applied at the point B. The point B is part of two bars CB and DB. These are connected to, rigidly connected to these points. And the orientation of this the slope is given by this triangles. And it is asked to determine the vertical deflection at the point B. And if you draw the free body diagram of the point B, it will be like this. A point, the load P will be acting downwards. The force on BD will be acting in this direction. BD, this is BD. And force BC will be acting in this direction. And considering the orientation, the slope of these BD and BC, we can draw the diagram, free body diagram, as a force triangle like this. The force P is acting like this, force BD, BC, using this, a force triangle can be drawn. And using the geometry of the structure, we can write BC equal to 0.6L and BD is equal to 0.8L. And L is the dimension of L. And from this geometry, we can conclude that BC is equal to 0.6L. BC, this length, is 0.6L and other one is 0.8L. So BC is 0.8L and BD is 0.8L. From the free body diagram of pin B and the force triangle, we get FBC is equal to 0.6 into P. From this diagram, we have this diagram here, say 3, 4, 5. These sides are in this ratio, 3, 4, 5, in that ratio. FBC, this length is BC 0.6 and this is 0.8L. In that case, this will be L. That is how we obtained these values. And using the same approach, you can say FBC is equal to 0.6 into P. P is a load which is applied, acting in this direction along the L direction. Line shown here. FED is equal to 0.8. This is only a free body diagram, and from the geometry of the diagram, we got these values. And FBD is acting in the downward direction. The direction also we have to consider. BD, actually it is acting in this direction, but we have taken it as the opposite direction. That is why we have to use minus 0.8. For the construction of this triangle, we have reversed that direction. And strain energy. For determining the strain energy, we use the expression, say, P square L by 2AE. P square L by 2AE. Here it is, force is 0.6 P. Here the length is 0.6 L. 2AE. Cross section is given the same material and the same cross section. So those two are taken as constant. Then contribution from one part. This is the contribution from the other part. And we'll multiply this and then add this together to get the total strain energy of the two components of the system, which is subjected to a single force. Strain energy from the part BC and BD. And this is a strain energy. And this is equal to the work done by the load. Work done is half of P into Y. By it is written as B at the point B. Deflection at the point B is given as YB. YB is the unknown. So this 0.728 by 2, that is we have taken as 0.364 P square L by AE. This one, this expression. This is a standard expression which we have taken from the previous slide. Half P into Y. Force into deflection. And from this, YB can be calculated as 0.78728 PL by AE. Since values are not given, numeric values are not given, we have to use it like this. If the numeric values are given, we can substitute the values P, L, A, E. All these are substituted. We will get the correct value of deflection, how much deflection is obtained. And this is how we carry out problems in solve the problems in using the strain energy method. Now that method is called work energy method. Work energy method is the approach we are using for a single load. Only a single load is applied. Multiple loads are applied, we cannot use the work energy method. And this is another problem which we're not having enough time to explain this problem. But this problem is explained in the textbook, and you can just refer to the textbook and see how the problem is determined, evaluated.
Okay. If moment is applied in set plane, which equation can be used? That's one of the question. And another question is, what is the difference between moment and torque? In which planes they are applied?
Actually, the moment is applied along the Z plane. If you consider this as the X and this as Y, moment is applied like this, and the moment is applied exactly in the Z plane or along the axial transfers to the axial direction. The moment is applied, and that is being considered here.
Thank you, sir, for this informative class.